Bismillahirrahmanirrahim. Assalamu alaikum friends. In today's video, we will be going to study about solar structures. As we all know that the demand of the solar structures and the solar panels are increasing day by day all over the world. As a structural engineer, it is necessary to understand the concept and mechanism of the solar structure, how to deal with it, how to analyze it, and how to design it. But before going to the detail of analysis and design procedures, it is important to know about what are the different solar structure types. Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends. And let's learn structural engineering together. One more thing, we have already started design courses related to reinforced concrete structures and steel structures along with the steel connection design. If you did not watch those videos, then please go and watch those. Links of these videos I am sharing in the description below. So let's get started. So first we will talk about the types of the structure. There are some categories. First we will talk about based on installation location. First one is the greenfield structures. Greenfield refers to an area of land typically unused or undeveloped where solar panels or other renewable energy infrastructure is installed. These type of structures are commonly installed in that particular area where there are big land is available and it can be utilized for solar structures, and the land must be unobstructed of the shadow. The second one based on the location is the rooftop. Rooftop structures refers to the installation of solar panels on the roof of the buildings or any other structures. Now based on the structural configurations. First type is the framed or braced structure. So look at these pictures. The structure is having framed behavior or braced in the main wind direction. So what does it mean? That the main wind direction is this one or this one. In this picture, this is the main wind direction or this is the main wind direction, right? So it is said that in this particular directions or these directions, the structure must be braced or is having the framed action. For example, in this structure we can see that these are the bracings, alright, and this is the beam and these are the columns, alright. So this is the frame having braced structure, and this is the frame where no bracings are there, so it is having the framed structure. It's a moment frame, and in this particular picture we can say that it is something like of a truss, so it is also a braced structure. Second one is the cantilever structure. The structure is having the cantilever behavior in the main wind direction. As we can see that in this picture, that this is the column supporting the beam having a single brace, but this brace is only for breaking out the unbraced land of the column, but the overall structural behavior is a cantilever behavior. Its deflected shape is like this one. Similarly, there is a monopole structure. Single pole is carrying the load of these panels, and this is also a cantilever type structure, and this is also a cantilever type structure. Alright. Now design loads for solar structures. First one are the dead loads, second one are the wind loads, and the third one are the snow loads. Dead load includes self weight of the structure and self weight of the solar panels. Wind load includes the wind loads, which is calculated based on the design code which we are following, and the snow loads also calculated based on the design code. We will do the calculations of dead load including the solar panel weights and we will do the wind load calculations, but we will not go into the snow load calculations. Typical solar structure elements. Now it is important to know what are the typical elements, structural elements in the solar structure. So this is a solar structure. First one are the purlins or the secondary beams. Purlins on which the solar plates are connected. Second one are the main beams on which the purlins are supported. Third one are the columns, vertical supporting elements which supports the whole structure. And fourth one are the bracings, elements for the lateral stability of the structure. Now, required data before structure design. It is necessary for the structural engineer to capture or to collect some data before any solar structure design. So what are that data? First, solar structure type, either the greenfield or the rooftop. Second one is the height. Third one is the array arrangement. Fourth one is the solar panel brochure or solar panel detail, which is to be installed at site. And fifth one is the site location. In the height, we will be interested to know the clear height under the structure. If the area under the structure need to be utilized, then we will know what should be the minimum clear height under the structure. And the second one is the building height if the structure type is rooftop. Third one is the array arrangement, which means that the number of rows of the panels and number of columns of the panels, means the total number of panels. First we will have to determine, and then we will have to determine in what array arrangement they should be placed. So number of rows m and number of columns n, m by n. This is the optional, because some client want that okay, we need this by this array of the solar panels, and some clients need, I want that particular kilowatt rating of the solar system. Now it's up to you how to utilize or how to arrange the solar structures, solar panels. In the solar panel brochure, we will be having the solar panel size, solar panel power rating, solar panel weight, and the panel connection hole details. In the site locations, why we want it? Because the location of the site at which the solar structure is to be installed for the wind velocity, which means that either the site is constructed at the area which is surrounded by some buildings, or is the area in the desert or something like that, main open field, and or near the sea. For the exposure classifications. Now the load transfer from the solar plate to the structure. So for example, this is a solar panel detail. Here it is written the size, outer size of the outer to outer size of the solar panel. Now these are the holes given. These holes are already punched into the solar panel frame itself, and these are given to install on the structure. It is recommended by the solar companies to install bolts in these holes. Other than that, they would be destroyed or they would be broken. So this spacing is 1600, the inner holes spacing is 1200, and the innermost spacing of holes is 400. But we did not recommend the closer one. Why? Because if we choose this 400, then the cantilever portion of the solar panel itself is very large. So it is better to connect either for this 1200 or 1600 or something, whatever, depending upon the solar panel company. Now the load transfer from solar plate to the structure. Since the solar panels are connected on the purlins via bolts, there are 4 holes utilized per panel. So the load transfer from solar panel, either the dead weight or any other area loads, uniformly distributed loads, are transferred via point loads or the joint loads. So this is the solar panels, and for example, this is the area load, this is the plan, and these are the holes marked. Total length of the array is L and width is W. Joint load is calculated as area load multiplied by the area. For example, the area load is 5 kPa, length and width is 4 by 2, total joints per panel is 4, total number of panels is 4, so total joints is 4 by 4, 16. Joint load per joint is 5 by 4 by 2 by 16. So it's 2.5 kilonewton. So these are the external joints and these are the internal joints. These internal joints, these two joints will be considered as one because they are very close to each other. So it is recommended not to apply the loads so closely. So just combine them and treat it as single joint. The joint load 2.5 is highlighted with yellow color, and these for these joints, and the joint load twice is for these joints, right? Now the solar panel orientation. First one is the portrait or P-type structure. Solar orientation in which the longer side of the panel is parallel to the structure slope. For example, here the structure slope is like this, shown in the green arrow, and the longer side of the solar panel is parallel to this slope. Okay. Similarly, in this particular picture, the longer side is parallel to this slope. Type 2 is the landscape or L-type structure, in which the shorter side is parallel to the structure slope. For example, in this, the structure slope is shown in the green arrow, and this is the shorter side which is parallel to the structure slope. Here it is also the shorter side parallel to the structure slope. Alright? Now, how to lay out the frame of the solar structure? For example, this is the solar structure. Scheme 1 is for purlins parallel to the slope. For example, we have selected the 2 by 2 L arrangement. It is said that 2 by 2 means 2 are the rows, first row and the second row, and 2 means column, first column and the second column. So there are 2 by 2, and L means the landscape orientation. So the first scheme is the purlins are parallel to the slope. For example, the green arrow shows the slope, and these are the purlins running parallel to the slope, and the main beams are perpendicular to the purlins, and these are the columns. This is the one scheme. Now the second scheme is purlin perpendicular to the slope. The same arrangement, but the purlins running perpendicular now, and these are the main beams and the columns. Now the disadvantage of this scheme 2 is that these two purlins are very close to each other, because as we have discussed that for the joint load calculations we will be considering these joints as single, but there is a separation between these two joints, so these two holes, so it is necessary to run separate purlins for separate holes and they are very close to each other, so it is economically not good. So scheme 1 is good economically. Now we will calculate the wind loads based on ASCE 716 specifications. Solar structure look like a monoslope roof structure. Like these are the structures having the roof as a monoslope roof, means a single slope roof. So the solar structure are look like these? No. Why? Due to the enclosure classification. What are these? These structures are enclosed or partially enclosed. You can see that there are the walls in these structures and there are some openings like doors, windows, and there are very little openings compared to the complete enclosed area, right? So these are the enclosed or partially enclosed structures. So what is the enclosure classification for the solar structure? An open structure, because wind can pass through the structure. When wind is first hit the structure and then can easily pass through the structure, alright? So that is why it is considered as the open structure. So design wind pressure equation for the open buildings with monoslope, pitched or the trough free roofs. So we are interested for this particular word, open buildings with monoslope roof. So the net design pressure for main wind force resisting system of an open building with monoslope, pitched or trough free roofs shall be determined by the following equation. P is equals to QH times GCN. QH is the velocity pressure, G is the gust effect factor, and CN, C subscript N, is the net pressure coefficient determined from figure this. So this is the figure 27.3-4 in which it is shown the monoslope roof and the coefficient diagrams and the wind load diagrams and all wind directions. So there are basically two main wind direction that is to be considered while designing these type of structures. The first one is the wind direction gamma equals 0, means that if the slope is this, then the wind is blowing from left to right. So gamma is 0. When gamma is 0, okay, wind direction is 0, then means that left to right. It is not dependent upon left to right always, because if the structure is like this one, so wind direction 0 is from this side, right to left, right? So it is necessary to understand the concept. Okay, so wind direction gamma is 0 from left to right here for this particular structure. And for this same particular structure, wind direction 180 degrees from right to left. Okay. Now what are the differences? We can see that the difference is the regions. When wind is blowing from left to right, then the upper portion gets windward and the lower portion gets leeward, L. And when the wind direction is 180 degrees, then the upper portion will get leeward and the lower portion will get windward. Okay, H is the mean roof height, which means that H is not the height from the ground to this point, but actually the height of the mean roof. It's the midpoint of the total structure. Okay, and L is considered as the horizontal projected area of the total array. Okay, and theta is the angle of the structure with the horizontal. Now these are the tables for the coefficients. It is written wind direction theta 0 and wind direction theta 180. These are the roof angles. It is remember to note that these coefficients can be used when H over L ratio is in between 0.25 and 1. Other than that, there will be some other procedures. We will talk about it later. Net pressure coefficient Cn for open buildings in theta must be less than or equal to 45. Greater than 45, there are some other procedures. Okay, now there are two load cases. Why there are two load cases? All the coefficients in the code are based on some experiments. So there are some wind tunnel experiments in which there are two load cases. So that's why load case A and B. We can see that it is written here clear flow and obstructed flow. What does it mean? It means that let's say we have a solar structure, elevated solar structure. Okay, and the area under this is obstructed less than 50%. So it is considered as clear flow. And it is great, and if it is greater than 50%, then it is considered as the obstructed flow. So we will have to pick up, for example, if our roof is having the angle of 15 degrees, so we will be considered for load case A direction 0 and direction 180 degrees. Similarly for load case B, direction 0 and direction 180 degrees. So there will be 4 load cases. Wind at 0A, similarly wind at 0B, then wind at 180A and wind at 180B. Okay, so these are the coefficients. Plus minus is similar as that we have discussed in the wind calculations video series, that negative sign indicates that the pressure away from the structure and positive sign denotes that the pressure is towards the structure, surface of the structure. Now there are some notes written under this figure which states that point number 1, CNW and CNL denotes the net pressures, contributions from the top and bottom surfaces of the windward and leeward half of the roof surfaces. Remember in our previous structures, let's say this is a structure, it's the wind is blowing from this direction, so it is a windward wall, pressure direction is this is a leeward wall, direction is this, and this is the roof, direction is this or that depending upon the theta. These are the external pressures, alright. There were internal pressure as well, positive GCPI and negative GCPI. Okay, then we will have to combine external and internal by the equation of algebraical sum and so and so. But here it is written that CNL and CNW, CN, it is here written CN. CN means net. It is, these coefficients are already being incorporated the effect of external and internal, because there is no concept for external and internal here. Why? Because the structure is open. The structure is open. So there is no concept of external or internal. Rather, let's say this is a structure. So when wind is blowing like in this direction, so it will hit the structure like this, and these vertices goes there and uplift the structure like on the upper surface as well. So there is a bottom surface, there is an upper surface. So upper surface pressure are different, bottom surface pressure are different. So they need to be algebraically summed to come up with the total net effect. So these coefficients shows the net effect of the upward and the bottom surfaces of the structure. So it is written here. The point number 2 is that clear wind flow denotes the relatively unobstructed wind flow with the blockage less than or equal to 50 degrees. And the obstructed wind flow denotes the objects below the roof inhibiting wind flow which is greater than 50 degrees blockage. Alright. For values of theta between 7.5 and 45 degrees, linear interpolation is permitted. We can see that there are the theta of 0, 7.5, 15, 25, 22.5, 30, 37.5 and 45. If our structure is having the slope or the theta in between, for example, it's 20. So we need to interpolate between these two. So the coefficients need to be interpolated, alright? So what the next point says, it's for values of theta less than 7 degrees, use the coefficients for 0. Okay. For example, there is written 0 and 7.5. So there is no need to interpolate between 0 and 7.5. Why? Because it is written that if the theta is in between 0 and 7.5, then use the value of 0. What is the third point? What is the fourth point? Sorry. Plus and minus sign signifies the pressures acting towards or away from the top surfaces respectively. All the load cases shown for each roof angle must be investigated. Means load case A and load case B. Okay, so these are the basic main points to consider while designing the solar structures. So in the next video, we will try to come up with the load calculation example problem, and in the later on we will model the structure and apply the loads on the structure and design it. If you liked our video, then please hit like and subscribe button and share as well with your friends. And you can comment below for your desired content or video. I will try to make that content for you. So this is up for today. See you in the next video.